Now that we know how to find a line of best fit, the next question is, how do we know it's actually a good line? How do we know it actually fits the data? And the measurement we use is called the correlation coefficient, which is often labeled R. It can be lowercase r or capital R, either way. We call it the R value, and it's a number that tells us how well the line fits the data. This value of this R is between -1 and 1. Generally speaking, the closer the value is to -1 or 1, the stronger the correlation. So if R equals 1 or R equals -1, it's a perfect correlation. What that means is all points in the data set lie on the exact same line. So here's two scatter plots. Notice that in both cases the y-axis is overall percentage, and then the x-axis is unlabeled, so we don't know what it is. We're told that one of these scatter plots has a correlation coefficient of 0.2, the other one has 0.72. Which one is the better one? Well, if I were to draw a line of best fit, I would suspect that technology would draw that one more or less like that, and then this one maybe more or less like this. So when I look at these two, I would say that this one is the 0.12 because the points are really kind of all over the place, especially this one. And then I would say this one is 0.72 because the majority of the points are fairly close to this line I've drawn through it, or a line that technology would draw through it. It is kind of important to be able to look at a graph and see, does it feel like it's linear correlated? But most of the time, we're actually going to have the data set, and we'll let the computer system tell us whether or not the values were correlated. The next question says, one of the scatter plots has each student's homework score for the semester on the x-axis and the overall percent in the y-axis. So one of these represents homework scores, which I would suspect is this one, because homework could be from 0 to 100, and I would guess that there is a correlation between how well a student does on homework and how well they do in the class. If you think about what happens with the homework values, number one, it's like study for exams, it's practice of the material we're going to test you over, and typically homework is a certain percent of the overall grade anyway, so there's definitely a correlation between the two. All right, the second one says, the other one is also overall percentage on the y-axis, but along the x-axis is the student's position alphabetically in the class. So the student whose name comes first alphabetically is 1, the next is 2, and so on and so forth. Well, just looking at the scale, 0 to 50, that means there's, based on this, there'd be less than 50 students in the class, which makes sense. So I would guess that this is the student position. And there's certainly no correlation that I have ever seen of the letter of your name, whether we use first name or last name, of the alphabet and your grade. I would guess it's definitely all over the place, and there would be no correlation. So this graph kind of helps visualize that. Okay, so what was the R value for the coefficient for the fast food sandwich plot? Well, we have that in Desmos. You could ignore all this diagnostics on mess. Who needs that calculator when we've got Desmos? So here was our data set. Here was the regression equation. Here's the R value. That R is equal to 0.9746. I'm going to write down the R squared value. We don't talk about it in this class, or it's not in our textbook, but I'm going to give it to you. That's called the coefficient of determination. And we can use that for nonlinear things. Boy, I can't spell determination at the moment. If you end up taking our 133, here we go, determination. Our 133 course, we go into great detail about this, about both of these. But for now, we're looking at just this value. And that tells us that it's a pretty good correlation. Our line does pretty well, and we already confirmed that with our prediction here. It was pretty close, so we're not too far off. All right, let me show you how to find this in Excel real fast. So let's open up an Excel document. So here's my Excel document. I've typed in the data for us. And the way we find the R value in Excel is we have to put in a graph. So we go into Insert, we select the values we're wanting to put in there, and we click Scatter Plot in this menu right here. So here's our scatter plot. This is the same picture we saw in Desmos. And if we want this to tell us the correlation coefficient, we have to click this. Now there's a problem because we don't actually get the correlation coefficient when we select this. I did that really fast. Let me do that again. So under Insert, we've got our graph in there, and when you insert it, clicking under the Design menu, you've got this quick layout in the top left. And I selected the one that has the f of x in it. What is this thing called? It's called Layout 9. And that has the equation. Notice this is the one we had, but it only has, what, 5 significant digits in it. And there's the R value, not the R squared value. So if we want, or sorry, the R squared value, not the R value. If we want the R value, we have to take the square root of that. So I'm going to hit equals. And then I'm going to type in square root, SQRT is the standard one, and I'm going to put in the 0.949, oops, yeah, 99, and there is our R value that we already wrote down. I suspect we could do some formatting in here, and we could find the format this to include the R value, but at this point I don't know how. So that's how we get this in Excel. I think it's just a lot simpler in Desmos, to be honest with you. So it's exactly the same, right, for 14 between Excel and Desmos, and a graphing calculator would give you the same thing as well. So how strong do you think the relationship is between the number of grams of fat in a fast food sandwich and the number of calories in it? We'd say maybe it's strong. There definitely seems to be a correlation. We could think about what could be some other things that can cause that, and I'm not a nutritionist. I don't quite know other things that cause calories, but I know there's other calories that come from things other than just fat. So the other question we're going to get onto is, what do we do with these lines of best fit? So in question 10, we calculated, recall that we made that prediction. And we got y equals 651.3727. That was our predicted value. And the actual value was the 660. So notice our prediction is below. And if we wanted to, we could calculate the relative difference and the actual difference between these two using our formulas from Unit 1. And you do that in the project. So the thing that we have to make sure that's clear in our heads is we are doing approximations and predictions. They are not exact values, not exact representations. So that equation that we wrote down will never give us the exact answer, but it will give us a good estimation of what's going on. So the next big thing in the textbook is asking you to do your shoe size and then your height, and then we would do create a line of best fit. But since we're in an online environment, that's going to be quite difficult to put together. So we're going to move on to the end of the section, the chapter, which happens to be all the way to page 160. And we're going to create a regression equation for these data. So notice this is a very common thing when we're given time. We reevaluate the time with an x value as being years since a particular time. So it could be years, it could be days, like in your project. You could do hours, whatever you want. And so our first known data value is 1900. We're going to call that time 0, and then the result is 718 here. This is the winning the gold medal links for the long jump for the Summer Olympics. So notice we let 12 years pass and we record another length, and we've got the x value here is 12. So the way we calculate this, if you don't know it right offhand, is you take the current year you're at and you subtract from it your starting year, and you get the result of 12. That will always work. So if we wanted to know what would our x value be for 2021, we would do 2021 minus 1900, and that equals what? 121. That would be the x value we put in our data set. Okay, so we're going to use Desmos to create this. And let's jump into Desmos again. And I think I'm going to start with a new graph because we got a big mess here. So remember, you click this plus sign and then you add in the table, and we're going to type our mess in. So I've got my data in there. And remember, if we want to see the picture of this, we click the zoom fit button right here, and there is the look of our data. Now, question 10 said find the equation of the line of best fit and round the coefficients to 3 decimal places. So here we go. Note that it's y1 in our table, so we'll type y1 tilde mx1 plus b. There's our equation, a slope of 0.0145157 and 7.17919. Now our author said round to, what did we say, 3 decimal places, so that would be 0.015 times x plus 7.179. Let's note also that r value, I think we're supposed to find it somewhere in there, so I'm just going to write it down. That's the 0.956. A pretty good r value. That's pretty close to 1. So here's our equation. We saw our scatter plot. What's the slope of the line, and what does it mean? All right, so the slope is this n value. And recall how we calculate slope. It's the change in y divided by the change in x. Well, y is the length of a long jump for the gold medal times, and x is years since 1900. So here's a sentence structure you can always write. For each year after 1900, so there we're talking, that accounts for the change in x, and it states that it's 1 change for each year. The gold winning long jump increased by 0.015 meters. So this value is really 0.15 over 1, so it's meters over years. So our line, the slope of our line is suggesting that the long jump is increasing by 0.015 of a year after 1900. Now, that can't actually be true because the Summer Olympics occurs every 4 years, not every single year. But this is how we get it into a unit rate. All right, so look at the second table. Here's some intermediate years that are not in this data set, 84, 2000, etc. And here's our x values. And here's the actual links. Let's use our equation, and we're told to use our equation to do a prediction. Well, I'm going to show you a nice trick in Excel, and not Excel, in Desmos to do this. So I'm going to write out the equation again, y equals, actually I'm going to do it like this. I'm going to say f of x equals 0.015x plus 7.179. And it just occurs to me that f of x is going to confuse you. So I'm going to call that j equals. All right, then I'm going to create a table. And in this table, I'm going to put a j. And I'm going to put in these numbers, 84, 104, 108, and 112. You know what? That's not working. What if I make this x? Will that make it work? There we go. So I labeled my equation as j equals, and then I changed the value in the table to be x to match the value in my equation, or the letter in my equation. And here, Desmos has done the calculations for us of all of those values. So all we have to do is write those down, and we can compare them to the actual time. So 8.493, sorry, the actual jumps, 8.7 8.39, 8.799, and 8.859. All right, so how good did we do? Well, you can see we're a little bit below on this one. Here we're a little bit above. Here we're getting quite a bit more above and even more above. So they're not great, right? How do the predictions compare to the actual jumps? They are getting worse. We might conclude that the line's not too awesome. The thing to think about is if we were to graph this line, it looks something like this. So if time were to go on forever, it's claiming that our jump length is always going to increase at this rate. So if we're like 100 years past, we're going to be getting crazy jumps. And I don't know, we'd have to think about what's going on with humanity if that were possible. Are we always getting stronger and able to jump further at that rate? Or, is that not really going to happen? And I don't think it is. All right, so then we're going to use our equation to predict the year that the men's long jump record will reach 9 meters. Well, note this is a Y value. So I'm going to teach you a nice trick in Desmos. We could solve this by hand, but we could also just do Y equals 9. Here's the line for 9, and let me hide all this other stuff so it doesn't distract us. Here's our prediction model. Where they intersect is what it's suggesting the value is. So the X value there is 121.4. Okay, so what is that predicting? Well, 121.4 years after 1900. So we'd add these two together and we get the prediction to be this year that we should be hitting it. Now we don't have the Summer Olympics this year, so it's not going to work. I think, or is it this year? I'm not sure. If we were to do a quick internet search, you'd see that in 1968 there was this crazy long jump that this guy did, and it would be an outlier. So it's 1968. He set the record, which wasn't broken until much later. I think he's in like the high 8 lengths.